All right. Let's go ahead and come together. Happy Halloween. I believe you have some sort of plan. My plan is to sit probably inside because it'll be raining, so I can't sit in the front yard. And we're going to push it through the rest of the time. I've got some work to do, and the dogs will be yelling intermittently during that time, so that'll be a really conducive walking environment. All right, so I think now that time has actually started, I'm going to reiterate the note that there's some extra credits right after this section in the notes. There's also a talk tomorrow evening. It's 4 or 5 o'clock. I can't remember which, and I don't remember where. So I'll forward you out an email indicating that there's a talk tomorrow night. If you go to that talk, take some notes, and then come by and talk to me, like Monday or something. We'll get you some extra credit. So I think the thing I want to open with is the loose end from last time. So I indicated last time that the Pythagorean identity lets you start with partial information about trig functions and turn that into complete information about trig functions. And here is exactly that example. So suppose I give you an angle theta, which is in quadrant 2. Let's start by drawing a picture. There's an angle in quadrant 2, and whose sine is square root of 5 divided by 30. Does that let me how could I encode that information in this unit circle picture? What thing on the unit circle gives you sine? The y value. And maybe we should start by reminding ourselves of that. So if you have a unit circle picture, so you start at 1, 0, you rotate by some angle, you get to the point x, y. Just remember sine, cosine, and tangent. Cosine gives you what? The x value. Sine gives you the y value. Tangent gives you? Nice. All right. So that means I don't know what the x value of this point is, but I do know its y value. Its y value is the square root of 5 over 30. All right. So let's plug along and see what we can do. So there's a relationship between sine and cosine called the Pythagorean identity that's in your notes at the top of this very page. Let's write down the Pythagorean identity and plug in the thing that we know. So the Pythagorean says that 1 is equal to sine squared of theta, so something squared, plus cosine squared of theta is always equal to 1. Between sine and cosine, which one do I already know? Sine. And maybe I'll try to write it in the same order as is up here. So the thing I don't know right now is cosine theta. I know what sine of theta is. It is root 5 over 3, and then that gets squared. And maybe I'll even propose one bit of simplification before we start solving. I want to know what cosine is. So cosine of theta is an unknown to me right now. So I think so I don't have to keep writing cosine theta. I am going to replace that with a variable name, perhaps C for cosine. So I'm going to rewrite that semicolon as C squared equal plus root 5 over 3, parentheses matter there, squared equals 1. That looks like something that's easy enough to solve for C. And depending on how comfortable you feel with things like fractions and squaring and square roots, maybe you feel uncomfortable with me to do stuff, maybe not. People want me to carry on and do algebra instead of just being quiet. Cool, but I will. So I want to solve that, so I want to get C on its own. What seems like a good idea to start with? I don't think I want to square root both sides because it it's c squared, and then it's plus and stuff. So if I take the square root of everything on that side, that plus is going to screw things up. Square root doesn't interact nicely with plus. So let's think about this in terms of the order that you do things in. So it looks like you start with c, then you square it, then you add a number to it. So the last thing you do in that process is you add a number. What undoes addition? Let's do that first. So it sure looks like then c squared is 1 minus root 5 over 3 quantity squared. And I want to hold off on doing more algebra for a moment. That thing on the right-hand side is like complicated looking, right? Does it need to be complicated looking? Yeah, we can expand that out and then simplify it. We could probably write that as a single fraction. How do you square a fraction? Squaring just means you multiply the thing by itself. So that means I need to think about multiplying a fraction by itself. Well, multiplying a fraction is easy, right? You multiply the numerator, then you multiply the denominator. Oh, cool. So this will be the same thing as 1 minus, you can square the numerator. What's the square root of 5 squared? 5? What's 3 squared? 1 minus 5 over 9. Does that simplify at all? What is 1 minus 5 ninths? All right, so this equation is now c squared equals 4 over 9. Does that look like something that's easy to solve for c? What do you want to do that? Square root. I'm going to do something slightly wrong, very wrong in fact, wrong enough that it'll screw up the answer. Anything wrong? Yeah, the plus or minus, and I think the plus or minus like really matters. So here's the takeaway here. Whenever you just use the Pythagorean identity to solve for cosine or sine, you lose that plus or minus information. You need to get it back somehow else. Is there something else that we've done that tells you whether cosine will be positive or negative? Will it be positive or negative? Negative. It's in quadrant 2. Nice. Square root 4 ninths, now let's just worry about simplifying. Does that simplify? Yeah, I can take the square root of the top and the square root of the bottom. What's the square root of 4? Square root of 9. So it looks like cosine theta is 2 over 3. Negative 2 over 3. Cool. We feeling pretty good about this? Is this enough information you can get at all the rest of the trig functions? Yeah, and maybe I'll follow the process where like I do one, you do one. So secant is given by 1 over the x coordinate. X is cosine, so that's 1 over cosine theta. That's 1 divided by negative 2 over 3. Oh, so there's like no geometry in this. It's just now how do you simplify that fraction? How do you feel about simplifying fractions like that? Anyone feel negatively like you want me to do it? Okay, cool. So it looks like I'm dividing by a fraction. Whenever you divide by a fraction, that means you want to multiply by the reciprocal. So this will be the same thing as 3 over negative 2. All right, the 1 is multiplied, so 1 times negative 3 over 2, but 1 times doesn't do anything. Any more simplifying that should happen? make the denominator simpler at the cost of making the numerator more complicated. So it could be negative 3 over 2. You can move that negative to the top. Neato. So what do you think? Will it be pretty similar to do the same thing for cosecant? So here's what I'd like you to do. Compute for me, if you would, cosecant theta. Collaborate with those around you. If you feel yourself getting stuck at any stage, raise your hand. I'll come on out. Oh, I guess you don't remember what gives cosecant. Well, it's probably in your notes on like a previous page, right? Shall we come together and see what we get? So, maybe let's just open with this. What did you get for cosecant of theta? Yeah. I hear a 3 square root 5 over 9. That seems more reasonable. Do I hear a second? How many people wrote down something like 3 divided by square root 5? Cool, you're not wrong. That is a correct answer. It's not fully simplified because it has a square root in the denominator. So maybe we'll just go through that walk. So if you got to the point of 3 divided by the square root of 5, well, now let's do all the walk. No point in skipping just one step. So cosecant is 1 over the y coordinate. So 1 over root 5 over 3. That's 3 over root 5. So dividing by a fraction means multiply by the reciprocal. I see a square root in the denominator. I don't like seeing square roots in the denominator. You should make the denominator as simple as possible because the denominator is the piece of a fraction that has the most complicated algebraic behavior. So you should simplify that. So I now see 3 root 5 divided by root 5 times root 5 is 5. Does that feel pretty good? And what do you think? Is this also enough information to find tangent and cotangent? Right, tangent is y over x, you know y, you know x. Cotangent is x over y, you know x, you know y. So, I'd rather move on and not spend time on the next two. Is there demand to do so? Neato. There will be some webbook questions in which you do. So here's what I want to do today, the new thing I want to introduce. There's another philosophy you can have about trigonometry, namely the thing that it's actually named for. Trigonometry tells us something about triangles. Right triangle trigonometry is a straightforward version to make sense of. So let's try to make sense of what these trig functions tell you about that triangle. And I don't know, how many people like already know what's going to go in the blanks at the bottom of this page? All right. So I want to also pick why those things are the right things to put in the blanks. So let's start with the philosophy of unit circle trigonometry. So here is a right triangle, but it's built into a unit circle. So what's the length of that hypotenuse of that right triangle? 1, right? The radius of the circle is 1, that orange length is a radius. The hypotenuse is equal to 1. The blue edge, the edge that is next to theta, that looks like it's the x-coordinate of the point at the end of the rotation. Right, it's how far to the left you go, that's the x value. So what is the side length of that adjacent side? Which trig function gives you the x value? Cosine. And I guess the other one now, process of elimination, is pretty straightforward. The length of the vertical side. All right, so here's the game I can do with this now. I'm going to take that triangle. I'm going to scale all of the side lengths up by a factor of h. Since this is all Euclidean geometry, that'll resolve all the angles. In like the non-Euclidean settings, weird stuff happens, but in a Euclidean setting, you can scale up a triangle and it resolves all the angles. So you take this triangle, you multiply every side length by h. What's the length of the hypotenuse now? Well, it used to be 1. I multiplied it by h. It is now h. What's the length of the adjacent side length now? It used to be cosine. I have now multiplied it by h. h cosine theta is the adjacent side length. What's the length of the opposite side? Nice. And this triangle is now basically any right triangle. Right? If you start with any right triangle, it comes from the result of this process by just figuring out what the hypotenuse is. Let's put a little square there to tell you it's a right triangle. Do those look like formulas you could solve for sine theta, cosine theta, and then figure out tangent theta? Yeah, so take a look at that. Tell me, what is sine theta equal to? You want to solve that for sine theta? Yeah. Opposite divided by h. h is hypotenuse. Opposite divided by hypotenuse. What about cosine theta? Nice. And it says here to use the tangent as sine over cosine to figure out tangent. But maybe here's a different plan. Tangent is the slope of that orange line. What's the slope of that orange line by looking at that triangle? Opposite over adjacent, right? It'll be rise over on. The rise is opposite, the on is adjacent. All right, so this is true now for any right triangle. If you start with any right triangle and fix an angle in that triangle, then trig functions at that angle tell you things about that triangle and conversely. And maybe it's worth just stating there are like a handful of different mnemonics you might have seen at points for these identities. Some of them are of questionable taste. So maybe I'll just go for one that I think carries enough information. If you can remember the syllables so, ka, and toba, you can remember these facts. Sine is opposite over hypotenuse. So cosine is adjacent over hypotenuse. Ka. Tangent is opposite over adjacent toa. So you now know where these formulas come from. These formulas are true because you can like scale NUI triangle back down to something in the unit circle and read off trig functions there. If you just want to remember like the statement, soka toa, and then cosine is C, A is adjacent, H is hypotenuse. That feel pretty good? All right, so here's the most straightforward example of using this. Here's a right triangle. Let's put the little box to indicate it's a right triangle. Let's suppose I tell you that its adjacent side length is 3, its opposite side length is 4. Is that enough information you can figure out all the trig functions? Yeah, and maybe ask the same question, like, I can talk, or you can just like do it and we'll come together at a moment. Do you want me to do anything? Cool, then I will. So I think the place to begin is let's walk out the hypotenuse. It's not the only place to begin. So by the Pythagorean identity, so what does the Pythagorean, well, I think I'd want to resolve the Pythagorean identity for like the trig function thing. By the Pythagorean theorem, this length squared plus that length squared is equal to the hypotenuse squared. So hypotenuse squared is equal to 3 squared plus 4 squared. And now we can just walk that out. Like, I guess eventually I'm going to take a square root. 3 squared is 9, 4 squared is 16, those add up to 25. So h must be the square root of 25. What's the square root of 25? So the hypotenuse has length 5. And we'll come across that same string of numbers enough times in this class that eventually you'll just realize, oh, if I see a right triangle, I see a 3 on one side, a 4 on the other, and then the hypotenuse is length 5. Or opposite, if you see a 3 on one of the legs and a 5 on the hypotenuse, you'll just know that the other side has to be 4. You can solve for it, but you can also just remember it. This is what's called a Pythagorean triple. A Pythagorean triple is a pair of 3 numbers, integers, so that the square of this plus the square of that is the square of that. It turns out there are infinitely many, and we'll see a few of them, and even ways of constructing infinitely many of them as we go through this class. Cool, we feeling good? All right. Is that enough information to now compute cosine theta? Right. So ka toa, cosine is adjacent over hypotenuse. What's the adjacent? 3. Cosine is adjacent over hypotenuse. Adjacent is 3. Hypotenuse is 5. If you really like fractions, that's 0.6. If you don't like fractions, 3/5 is fine. Sine of theta also easy to walk out now? What is sine of theta? I hear a 4 over 5. Do I hear a second? Nice. Do I hear a call for me to just like slow down a bit so people can like do the math on their own right now? All right. Tangent is nice. Opposite over adjacent. Groovy. That feel pretty good? So, trig functions are related to side length in a triangle. Oh, I should put that on the board now because I'm going to use it on the next page. Cosine is equal to the adjacent divided by the hypotenuse. Sine is equal to the opposite side length divided by the hypotenuse. Tangent is equal to opposite over adjacent. What I'm going to do now is absolutely and completely an applied problem. They're going to be like real numbers and measurements that I'm about to take live. I want to determine the length of the height of that wall. And here is how I will do it. I'm going to make some angle measurements from my eye level, which I'll have to determine, I guess, down to the bottom of the classroom and up to the top opposite corner of the classroom. the tool I'm going to use to do that is called an Avenue Level. I have purchased at some point the cheapest one I could find on the market. I think it cost me $15 on Amazon. There's no reason that you should buy one of these yourself unless you have occasion to want it. Let's use this. So what does this thing have in it? It's got a looking tube that you can look through. It's got a little dash in the middle so you can actually point it at the thing you want to. It's got a rotatable dial that has measurements in degrees. And it's got a little leveling bubble with a mirror so you can see it. So, let's use this. I'm going to stand right here and record some angle measurements. I would like people to record them because my memory is very bad, and if I get up and move, it'll screw up the measurements for the next thing. It's important you stand in the same place when you do this sort of thing. So, the angle I'm getting to the bottom of the classroom is an angle of decline 10 degrees. I'm now going to look from here up to the top of the classroom. I'm getting an angle of incline of 12 degrees. Now I need to record the height of my eye line because that'll be relevant for this diagram. The way I'm going to do that is a way that might feel pretty haphazard and sloppy. There's my eye line. I mean, better that than trying to hold the tape measure up to my eye. So this principle that I'm following is the same thing as is used by 70 issues. This is the same principle as is used by the surveyors you see measuring heights of buildings or heights of trees and stuff. They have a device on a tripod. That device on a tripod records how high up it is. It also records the angle of elevation at which it's pointing at something. It might also have one of these laser rangefinders, which is also built on top of trigonometry. Or it might not. You can figure that out on your own. Figure out the distances on your own by using the stuff we'll do right now. All right, so let's encode some of these measurements in this diagram. And I'm going to start by having you remind me of the angle measurements. When I looked to the top back of the classroom, so the upward angle, what number did I get? 12 degrees. Downward I got 10 degrees. I'm going to fill those in on this diagram. So my eye level was at 70 inches. The angle of decline to the bottom of the classroom was 10 degrees. To the top of the classroom, I got 12 degrees. So from here, what's the game? Use things you know about triangles and rectangles and shit, and then also SOHCAHTOA to figure out as many side lengths as you can. As soon as you have enough information to know the side length opposite, then you win. And maybe I'll start by labeling these points so we can refer to what edge we want to talk about. I'll start there and go counterclockwise. So there are a bunch of labeled points now. So by looking at this diagram, don't try to go all the way to the end all at once. Just tell me something that you could now compute in this diagram. It does that sometimes. How about this first? Like, this angle was at horizontal, right? All of those were compared with horizontal. So that's a right angle, that thing I just drew in dashed as a box. So could I figure out the angle AFB? Yeah, what is that angle? 80 degrees. It's an angle which, when added to 10 degrees, gives you 90 degrees. All right. And maybe I'll give the following hint as you go through this process. I don't want to find any hypotheses. So I won't bother finding any hypotheses, they just won't matter in my computation. Finding them wouldn't be wrong, but they're just not going to matter. Let's start trying to figure out if we can find a side length. So the only things that I think I can do that'll find me side lengths is use the fact that opposite sides in a rectangle are equal, and SOHCAHTOA. So, and looking at this using those two facts, is there a side length that you can just know now? What side length are you thinking of? CB. What should the side length CB be? 70. It's opposite 70, and that's a rectangle. I guess there's a built-in assumption here. I'm assuming that that opposite wall is actually a vertical wall. I mean, there's no such thing as a perfectly vertical wall. But probably how far off that wall is from vertical is way smaller than any of the other measurement errors in the measurements I just took. All right. Any other side length we can figure out? So maybe I'll say this. The philosophy of SOHCAHTOA says that if you have a right triangle, and on that right triangle you know an angle and a side, then you can figure out all of the side lengths in that triangle. Because if you know cosine of theta and you know the hypotenuse, you can solve to get the adjacent. So think in terms of that philosophy. Is there a side length here that you can now figure out using SOHCAHTOA? Which side length are you thinking of? That was all just very quiet. I think I heard 2 letters said, but I couldn't hear them. Let's see, I know this side length. So I think this triangle looks like a triangle that could be useful. I said that I gave you the bonus information that I wasn't going to try to find any hypotenuses. Is the law of hypotenuse hypotenuses? It sounds like something that's from the Latin, and Latin has weird pluralization rules, I think. So let's try to find that bottom side length, that side length from A to B. What trig function looks like it might be useful? So I said I don't want to find any hypotenuses. So I want to find this side length that is opposite 80 degrees. And I know the adjacent, so something that involves opposite and adjacent would be useful. Which trig function is that? Tangent. So let's write down that equation. Tangent of 80 degrees. Ooh, maybe I'll make up a variable name. Let's call that side length x, so I don't have to write like the side length from A to B over and over again. Tangent is opposite over adjacent. What's the opposite side length? It is the unknown side length x. What's the adjacent? 70. And maybe I'll record the inches. If you want to drop the units, then that's your business. That looks like something you can solve for x. I think so. Go go ahead and solve that, folks. If you've got a calculator, I think decimal approximations are not unwelcome. Oh, yeah. So make sure you're in degree mode. These angles are in degrees. And even if you don't have a calculator, you can get me like the exact value, which is what I'll want right now anyway. This isn't the final answer, so I don't care that much about the decimal approximation. I'll still record it. So what is x? Nice. Let's get a decimal approximation just so we can see if it looks reasonable. Based on the errors I have in my measurements already, let's stop at the whole numbers. I don't think I trust anything up to there anyway. Round correctly to the nearest inch.
Okay, 397.
Do I your agreement? Nice. So apparently the depth of the classroom is about 397 inches according to this measurement. And in fact, at the end of the previous section, someone was feeling dubious. So they actually checked the diagram for the classroom, which has like a scale on it that they found, indicated that the depth of the classroom is 384 inches. So that's not so far off. Based on all of the, like, how trustworthy you think any of the other things I was doing so far, I think that's accurate enough. Plus, built into that was trying to translate that scale, which is in like 3/16 of an inch is a foot, so I had to actually measure that. Anyway, we know x. Is x what we wanted to know? No, I wanted this whole length. So what can I do? We can just like keep finding side lengths, right? What's another side length on this diagram that you can just know? Well, that you can either figure out or just know now. Say louder. BD. ED. I agree. What's the side length of ED? Nice. It's the same as this. And maybe that one is too. Right, all of those horizontal side lengths, right, they share their edges of a common rectangle. So they all have to be the same. And they're all about 397 inches, but I don't have to keep writing 397 inches on the diagram, so they're just x. I know what x is. All right. That's not the side length I wanted either, but I think it's progress. Do you see a triangle containing a side length you know, and an angle that you know that you can now take advantage of? Which triangle are you thinking of? Triangle DFC. Cool. I know this angle, it's 12. I know that side length, it's x. So, there's a side length that I can figure out. I said I don't want any hypotenuses. So that's the only thing on the list. What trig function looks useful? Tangent. Right, all the other ones involve the hypotenuse, and I gave you the secret information that I don't care about hypotenuses. If you didn't have that, then you might go around finding hypotenuses, which would be fine. It's just, there's an easier path. So let's see, tangent of 12 degrees is opposite over adjacent. What's the opposite side length? I guess let's make up a name for it. I'm not very creative. Is y is opposite. What's the adjacent? It's whatever that is. For now I'll call it x because that's less to write. That look like something you could solve for y? Yeah, so let's do it. Y is equal to the tangent of 12 degrees multiplied by x. I know what x is. I'll use the exact value because it's just better practice to use exact values in a computation. There are great big measurement errors at the start, so it's not going to cost me a noticeable error on top of those. But you should use exact values when possible. So tangent 12 degrees multiplied by tangent of 80 degrees coming from the x times 70. All that is x. And now I can get a decimal approximation. And I could do, or I can wait for you to do. Should I do? All right, let's hear it. What is that? Like that? I don't believe that.
That doesn't see it.
Oh, that's in feet.
Oh, 84 inches.
Yeah, let's walk in inches because everything's in inches. Do I hear a second for that? I didn't do the computation myself. Okay, 84 inches it is. All right, is that enough information that we can figure out the height of the opposite wall? Yeah, I guess the fancy tool to use is addition. So we know this side length is about 84 inches. That's 70 inches. So the length of the side from B to D, which is what we want, is, that's notation I haven't used in the past, but edge from B to D, BD with a bar on top seems reasonable enough. Put some absolute value bars around because that like measures the size of something. Is equal to, my height 70 inches plus 84 inches is 154 inches. All right. That feel pretty good? So here's a useful tool. Right triangle trigonometry lets you take measurements that you make right here and translate these measurements to measurements over there. So you can take measurements non-locally and get distant values out of it. And this is exactly like when people talk about measuring the height of really tall trees, this is what they do. They don't like climb the tree and then drop a tape measure down. They stand a known distance from the tree. They make some measurements where they are, including some angle measurements. Then they use trigonometry. Groovy. So there's one other thing that I want to do with right triangles right now. And it's another very applied feeling thing. But the application will be opposite. Instead of applying trigonometry to triangles, I'm going to apply the philosophy of triangles and trigonometry to filling in the units auto. Oops, that's the copy I've already filled in. That's the other section. So my intent was that by the end of today, I would have all of these entries in quadrant 1 filled in. I think at most I'll get 45 degrees done. And let's try to figure out how to walk that out using right triangles. Here's how we'll do it. So I guess we'll start by remembering what we do know. Cosine of 0 is 1. Cosine of 0, 0. Tangent of 0, 0. Pi over 2 we also know. Cosine of pi over 2. Sine of pi over 2. Tangent pi over 2. Undefined because it'll be 1 over 0, which is not something you can make sense of. Let's start by trying to figure out trig functions at an angle of pi over 4 radians, which if you like is the same as 45 degrees, but I'll walk in radians. And here's the idea we'll use. Here's a triangle. It's got an angle of pi over 4 in it. So that means that if I can know things about this triangle, I can use SOHCAHTOA to figure out trig functions at pi over 4. I'll arrange that it's a right triangle so I can use SOHCAHTOA. That means that angle should be a 90-degree angle, pi over 2 radians. I'll set the hypotenuse to be 1, just so I don't have to have everything divided by some hypotenuse length. So if I could know the adjacent side length and the opposite side length, I could use that triangle to figure out trig functions. So let's try to do that. And let's start with this. I bet I have enough information to figure out that angle that I've called alpha there. Because what do angles inside a triangle have to add up to? I think I just want some right things, but 180 degrees. I'd rather walk in radians because everything else is in radians right now. How many radians is 180 degrees? Pi. Halfway around the circle is pi. Ooh, that means that this angle, pi over 4, plus that angle, pi over 2, plus this angle, alpha, have to add up to pi radians. Now looks like something you can solve for alpha. What's alpha? Well, you can do it algebraically, but maybe I'll do the visual computation. That looks like a unit circle, but I just want that whole circle to represent pi. Well, that means I have a quarter of a pi plus a half of a pi plus an unknown angle adds up to 1 full pi. How much of pi is that? A quarter of a pi? Does that agree with what the algebra gave you? Nice. Should I actually do the algebra? All right. Ooh, that means this angle is pi over 4. And here is the thing to notice. Those two angles are the exact same angle. They have the same bigness to them. Whenever you are in a situation where you have a triangle and two angles are the same, that means the sides opposite those angles have to be the same. This is now an isosceles triangle. So, these two side lengths have to be the same. So A has to be the same as B. Cool. So it looks like in that diagram I could either replace the A with the B or replace B by A. I think I'd rather have A's in my diagram instead of B's. It doesn't really matter. The opposite side length is A. And let's just see what we can find right now. Maybe I'll start with tangent. So let's see, SOHCAHTOA. Tangent is opposite divided by adjacent. What's the side length opposite pi over 4? A, because B is equal to A. What's the side length adjacent? Oh, cool. So what's tangent? All right. I can now fill an entry in this unit circle. Tangent of pi over 4 is 1. To get the last two, well, cosine is adjacent over hypotenuse. That will be A divided by 1. Looks like I need to know A. Is it easy to find A in this diagram? I think I can even do it. Let's do the algebra, but with some speed. The Pythagorean theorem says that A squared plus A squared is equal to 1 squared. Let's yada 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 the algebra. And we will get A equal to square root of 2 over 2. I told you to stop. So A is root 2 over 2. So what's the cosine of pi over 4? That number equals root 2 over 2 Sine will also be root 2 over 2. So with that, we now have justification enough to fill in those two remaining blanks. Stefan at the end got like speedy. So at the start of class tomorrow, if you want to ask me any questions about this, that's a great thing to start class with.